Alcohols are organic compounds which contain the hydroxyl moiety. R here typically represents alkyl groups. The oxygen in alcohols contain two lone pairs, and this lone pair, together with the bonds, form a tetrahedral electron group geometry around the oxygen atom. The oxygen in alcohols is sp3 hybridized, and the geometry of atoms around oxygen is bent or V-shaped. Alcohols may be methyl alcohol or methanol. Primary alcohols, such as in this case here is ethanol or ethyl alcohol. Secondary, such as 2-propanol or isopropyl alcohol. Tertiary, for the case of 2-methyl 2-propanol, or more commonly known as tertiary butyl alcohol. Alcohols may be benzylic, such as this one for benzyl alcohol, or allylic, such as this one for prop 2-in-1-ol. Also, alcohols can be diols, where two hydroxy groups are present in a molecule. This compound here is called propane 1,2-diol or propylene glycol. Alcohols are prepared by hydration of olefins formed by thermal cracking of petroleum. Hydration of olefins or alkenes have already been discussed in our previous topic. A common source of ethanol is the yeast fermentation of sugar. Molecules of alcohols form hydrogen bonds to each other. Hydrogen bonds are strong intermolecular forces that give molecules high boiling points, such as the case here for ethanol. If you would compare these three compounds, propane, ethanol, and ethanol, their molecular weight are very close to each other, but their boiling points are very different. This is because of the intermolecular forces that occur between these types of molecules. For propane, the major intermolecular force is dispersion forces. Ethanol has a dipole moment from this carbon to this oxygen, and so this molecule has dipole-dipole interactions with each other. Dipole-dipole interactions enable ethanol to have a boiling point of 21 degrees Celsius compared to the boiling point of propane. However, the boiling point of ethanol is still so much higher. This is because of the hydrogen bonding between molecules of this alcohol. This is also the reason why low molar mass alcohols are soluble in water. Alcohols can form hydrogen bonds with water molecules. Still, as the size of the nonpolar component of the alcohol increases, its solubility with water decreases. To name alcohols, we select the longest chain containing the hydroxyl group and change the end letter E of the parent hydrocarbon to ol. Thus, this compound is named as 1-propanol. This is 1-propanol because the hydroxy group is connected to the terminal carbon of the propane chain. In IUPAC, propan 1-ol is also an acceptable name for this compound. We also give carbon with OH the lowest possible number and locate other substituents accordingly. This compound here is named 2-propanol or propan 2-ol. For longer chains, such as this one, we immediately give the hydroxy group the lowest locant possible In this case here, we give it a locant of 2. The methyl group has a locant of 3. Thus, this compound is named as 3-methyl-2-pentanol or 3-methyl-pentan-2-ol. What about this one? Since this is an alcohol, one position will be given at this carbon, and the other groups will be at 3 and 4 positions. The name of this compound is 4-chloro-3-methyl-1-butanol. Common names of simple alcohols are often used and are approved by IUPAC. The names ethyl alcohol, isopropyl alcohol, and T-butyl alcohol are familiar to you. Diols have 2 hydroxyls. They are called glycols in common nomenclature. This compound here has an ethane backbone, and the hydroxyl groups are at 1 and 2 positions. So we call it ethane 1,2-diol. The common name is ethylene glycol. This other compound again has hydroxyl groups at 1 and 2 positions, and so is named as propane 1,2-diol or propylene glycol. Because of the electronegative oxygen, the hydrogen attached to oxygen is acidic. The protonation leaves behind an alkoxide. The pKa of alcohols is around 16 to 17. Hence, if we consider the conjugate bases of these acids here, these bases are capable of removing a hydrogen in an alcohol. An example is sodium amide. Ammonia, having a pKa of 38, will have a conjugate base that is relatively stronger compared to the conjugate base of alcohols. Thus, it will react via an acid-base reaction and take this proton to give ammonia and the alkoxide. Other agents that will also work in this case are the alkynide with a pKa of around 25, the hydride, the active metals such as lithium, sodium, and potassium. If you mix these metals with alcohols, they will readily form the alkoxide. Grignard reagents are also very strong bases that are perfectly capable of removing the acidic hydrogen of alcohols. The more substituted the carbon attached to the hydroxyl group, the less acidic the alcohol. If we consider these 3 compounds here, they all contain 4 carbons, hence are isomeric. Their pKa increase with more substitution of the carbon attached to the hydroxyl, the highest of which is for tertiary butyl alcohol. This can be explained by the low stability of the tertiary butoxide. This is the conjugate base of tertiary butyl alcohol. This is less stable because it is less solvated. Polar solvent molecules will have difficulty solvating this anion because of the large groups that are surrounding it. Solvation gives stability to anions, and because of this, the formation of this anion is less favored compared to the formation of the alkoxide in 1-butanol. Electron-donating groups decrease acidity, and electron-withdrawing groups increase acidity. As you see in this example, fluorine atoms in an alcohol makes it more acidic. The reason for this is inductive effect. Inductive effect is the tendency of atoms or groups to pull electrons towards themselves via the sigma bond, and in this case, reduce the intensity of this negative charge on oxygen. The more electron withdrawing groups, the more tendency for this negative charge to be reduced. This reduction equates to the stability of this anion. And so, two fluorines right next to the hydroxyl group makes this compound more acidic. And if the fluorine is reduced or moved far away or removed altogether, the acidity of the alcohol will decrease. Inductive effect is affected by distance, so electron withdrawing groups that are farther away from the hydroxyl group will have lower effect on the stability of the negatively charged oxygen.